Oh, one for like the lab where you're doing it, and then one for doing that now. Oh, so it's like lab in class. Yeah.
All right.
Yeah, but it's like lab, and then lectures, she just kind of talks about it, but then halfway through, it's like only the questions, but you still have to go. Yeah.
Okay, let's keep going. Are you guys happy you ate? Feeling
Yeah.
better? All right, that's good. All right, let's continue. Carbohydrate, just a little bit. How do we measure total carbohydrate? Is there a method that allows us to measure total carbohydrate? Why is that? Because total carbohydrate are difficult. No, because why? Why isn't there one method that can measure total carbohydrate?
Because there's a lot of different carbohydrates.
There are a lot of different forms of carbohydrates. Some are simple forms, sugars, small monosaccharides, and some are complex, like starch. Some have completely different components, like dietary fiber. So there is not one method that gets them all. So how do we get total carbohydrates for a food? Because we need it on the label. So how do we get total carbohydrate for the label? Subtracting it. So that's why we did all of these approximate analyses tests. And then one of the questions in the lab report is determine total carbohydrate. So you're going to get 100 and subtract all of those different components, as moisture, fat, protein, all on what basis though? 100 minus everything else on what basis, you would get the total carbohydrate on what basis. Okay, but if you have a simple sugar and water solution or beverage, we do this assay that you will do next week, which is the phenol sulfuric acid method. Okay, so often or many times when you have a complex food product, there are a couple of important steps that you need to do before we can analyze different components of carbohydrate. Number one, you get your food sample. It has to be representative of the lot. It's homogenized. Then what? If it has higher than 10% moisture content, you dry. Very good. Second, if it's high in fat or relatively high in fat, we defat. So these two steps are often done before we determine starch, dietary fiber, or carbohydrate components in general to avoid any interferences. Remove the water, remove the fat, continue. Okay. Then we talked briefly about the different methods to analyze mono, di, and oligosaccharides. We categorize them into colorimetric methods, chromatographic methods, and enzymatic methods. So I'll spend a little bit of time on all of these different types of methods. Very close to the board. Or is it just me? Okay. So when we have a complex food matrix and there are so many different components, you remove the water, you remove the fat, and then you have your monodioligosaccharides that you want to analyze, but you also have starch, protein, fiber. So you just want to extract the monodi and oligosaccharide as number one or number three after drying and defatting. So the most common way of doing that is by solvent extraction. 80% ethanol with heat. So what you see here is a simple reflux apparatus where you put your sample that is dried and defatted with 80% ethanol, and then you put it on a hot plate, but you also have a condenser here where you have a circulating water, cold water in and out. So what happens here is, your ethanol is going to evaporate, and instead of drying out the sample, so you condense it So you can reflux about an hour to 2 hours to solubilize your small sugars, monodi and oligosaccharides. Then what remains insoluble is are your starches, proteins, dietary fiber. So you filter and you get the 80% ethanol that has now the sugar in it, and you also the rotovap in one of the labs. So the rotovap is you put your 80% ethanol with the sugars now, and you want to concentrate, so you remove the ethanol by just under vacuum and collecting with condensation, collecting your ethanol water, and then now you have the sugars in this flask. So you just add to it whatever solvent necessary for the next step for quantification. It could be just water, it could be another solvent that you're using for an HPLC determination, and so on. So this is the most common method to extract those small saccharides and separate them from other complex compounds like polysaccharides and proteins. Another less common method, they call it the Karas treatment, which is basically, in this case, you put a reagent, and that reagent will cause protein, starch, and colors, will capture colors, as well to precipitate, and then everything that remains in solution would be your saccharides. It's less common process. Okay, so now that you have your sugars, monodi and oligosaccharides, then you can start looking at different methods of analysis. The most common colorimetric methods used are basically based on reducing power of the sugars. So your monodi and oligosaccharides have essentially a free carbonyl carbon that will act as a reducing agent. So in the presence of alkaline or in an alkaline solution, your reducing sugar would reduce cupric ion to cuprous. And the cuprous will react with a specific complex reagent, and then you would determine quantitate via gravimetric. You just weigh out the precipitate, or you titrate, or you measure a color change by spectrophotometry. So basically, the cupric ion will give you this blue color, and then in alkaline and reducing sugar, you will get a cuprous oxide precipitate, and it's red. So you can take that precipitate, dry it, and weigh it, and then determine gravimetrically the reducing sugar content by doing standard curves, obviously. So it just, the precipitate will be red. Here's just, it's just to illustrate that if you end up with a really dark color that you cannot see a precipitate, that means your solution is really concentrated and you really need to dilute so that you have less precipitate that you could separate. And that's all what it's demonstrating. So there are many different methods used. The most common is Muji-Nelson method, but every method has the same principle. All these three methods have the same principle. You have cupric reagent that would reduce the cuprous, and then the cuprous would be either reacted with the reagent, or it would be measured gravimetrically, or we titrate, or we measure spectrophotometry using a spectrophotometer. When it reacts with arsenomolybdate, this is your Muji-Nelson. That's the most common. Is in alkaline solution, your cupric is reduced to cuprous. It reacts with arsenomolybdate reagent. It gives you a color that you measure at 520. That's the most common method to use. Of course, you're not really going to memorize any of this. What I'm demonstrating is these methods have the same principle, reducing cupric to cuprous, but then each method have a different way of determination. The most common is Moody-Nelson, and it uses arsenomolybdate as a reagent, and then you measure a blue color absorption of blue color. That's what it is. All right. So this is the redundant question. The answer is on the slide. What carbohydrate do you analyze using the Moody-Nelson method and other reduction method? Really reducing sugars. Good. So sucrose, is it reducing sugar? It's not reducing sugar. The carbonyl carbon is in the glycosidic bond here between glucose and fructose. Okay. So how do we analyze sucrose? Following this method.
We break it down.
We break it down. So we use acid and heat, break down the glycosidic bonds, then we free glucose and fructose, then we determine the reducing power of these two reducing sugars now. There's always an SOP to follow with the exact reagents and steps of the reaction. Okay. Other common approach for determining mono, di, and oligosaccharides is enzymatic method. So enzymes are proteins and they're organic catalysts, basically. So they catalyze the conversion of substrate to a product. So often your substrate in this case will be the sugar, either glucose, fructose, sucrose, maltose, whatever it is, will be your substrate, and you will use an enzyme or a combination of enzymes that will aid in production of a product that you often use spectrophotometry to analyze. So you use this enzyme to convert a substrate into a product that you can measure the absorption of light and then quantitate that substrate, which is the sugar. So the enzymes will have high specificity to that particular substrate, and we'll give you a few examples here in a little bit. So the enzymes are used to determine a particular constituent. So the constituent, the sugar, will be your substrate. And we want to make sure that the reaction is not inhibited by any potential inhibitors, and your solution needs to be clear. So we need probably make sure that it's centrifuge and you have it clear because you measure absorbance by spectroscopy. Okay, so oftentimes these enzymatic reactions are coupled reaction. Have you heard of this term before? Coupled enzymatic reaction. That means you have at least two enzymatic reactions happening because the first one gives you a product, but it doesn't give, there's no color or there's no absorption of light. None of the substrate or products absorb light, but it's kind of the initial stage of the reaction. Auxiliary reaction are also called measuring reaction. So your food substitute or constituent substrate, which is a sugar, any sugar in this case, will react in the presence of the enzyme to give a product. But still, we cannot measure absorbance of light. So another reaction is important, and it's called an indicator reaction with another enzyme. Then your product from the first reaction will react to give you a product that will absorb light. So in this case, either the reactant C or R or S will absorb light. So there's an example of glucose and the use of two enzymes. The first one is hexokinase. So basically your glucose reacts with ATP to give you a product. In this case, glucose 6-phosphate. This product will be used in a second reaction with dehydrogenase, glucose 6-phosphate dehydrogenase, reacts with NADP. So basically, we're removing a hydrogen, and we're producing a product which we don't care for. We care for NADPH that will absorb light at a particular lambda that we will be measuring. Okay, so that's an example. There is another coupled reaction for glucose. I'll show you in a little bit. Okay. So many applications, we can use enzymatic reactions to measure fructose, glucose, galactose, or oligosaccharides, lactose, maltose, sucrose. And the good thing about them is that there are so many enzymatic kits that we can purchase. And just it comes with instructions and we can follow, and it's very easy usually to follow, and we get our concentration of the sugars in question. Commonly also enzymes are used to determine polysaccharides like total starch, or even total percent amylose and total percent amylopectin. And I'll show you those series of enzymes later under the starch analysis. So many advantages. Enzymes are specific, so they catalyze a specific conversion of the substrate to a product. Like I said, commercially available kits, so you can buy them. They're cheap, reproducible, easy to follow, and generally are sensitive and have low threshold. So you can determine concentrations at very, very low concentrations. Now, among the disadvantages is sometimes, because it's an absorption method, if you have components in your sample that might interfere by absorbing at the same wavelength. So that can potentially be a problem, which will necessitate you doing different ways of formulating your standards, like standard addition, for example, that we talked about under spectroscopy. And not always 100% specific, not because the enzyme is not specific, but sometimes the enzyme is not pure. So the enzyme might come in with some contaminants of other enzymes that will cause a little bit of erroneous results due to not being 100% pure. The purer the enzyme, the more expensive it is. All right, any questions for moving on to chromatographic methods? Okay. So very, very briefly, sometimes we use a planar chromatography, paper or thin layer chromatography. This is a qualitative method to look at what we have, but it's very rare, not commonly used. And here's just an FYI example of paper chromatography that is used to separate small molecular weight sugars, what's the stationary phase and the mobile phase, FYI. But I'm not going to spend time on that. So moving on to the juicy stuff, where we use HPLC as a method to identify and quantitate small molecular weight sugars. So monosaccharides, disaccharides, and oligosaccharides. So here we're going to bring back chromatography in an applied manner and look at how we can use normal phase, reverse phase, anion exchange, and cation exchange for the determination of mono, di, and oligosaccharides. Bring back nice memories of chromatography. No? Emma, why? What's that? Too many types. Yes, that's true. So yeah, but we'll remind you of chromatography a little bit and the use of the different types in this particular application. Let's start with normal phase. So normal phase, what's your stationary phase? Polar or non-polar? Polar, very good, very good. So, and then your mobile phase would be non-polar. Wonderful. So, normal phase, in this example, we say unmodified silica. We will get strong interactions between the silanol groups from the silica and hydroxyl groups from the carbohydrate. So the reaction is really strong. So we basically barely get any separation. So separation is impossible. So now what? We modify the silica. So we use chemically modified silica. Do you remember HILIC? Hydrophilic interaction liquid chromatography. So when we modify silica with a group that is, it remains polar, the stationary phase remains polar, but now it's modified. We call it hydrophilic interaction liquid chromatography. And this particular example is you modify the silica with amine group. So amine bonded stationary phase. So you have your silica interacting with an amine group. And in HILIC, your mobile phase is not a pure organic that is immiscible with water, like hexane. It is miscible with water, but it's still nonpolar. So 50 to 85% acetonitrile, so it still has some miscibility with water. And we can adjust the column temperature to enhance separation. So the principle of separation, so you have your silica, you have your amine group, so you have nitrogen bonded to hydrogen, and then the sugars have OH groups. So you will have then hydrogen bonding between OH groups and amine group, and that's the form of interaction that happens. Okay, with this form of interaction, the more hydroxyl groups you have, the more interactions you have. So lactose, because it's a disaccharide, it will have more OH group, will elute later on than a carbohydrate, a smaller carbohydrate with less OH group. So the retention is based on how many OH groups you have. The more OH groups you have, the more interaction with the amine groups, the longer they stay on the column. All right. So because these are sugars, most of the detectors or the main detector used is RI detector, refractive index detector. We cannot do gradient elution. Do you remember why? With refractive index detector? Do you remember what gradient elution is? So what is it? What do you remember? Exactly. Over time, the mobile phase changes concentration, so it's not the same. So what happens to the refractive index? Changes as well. So the baseline is changing, so it makes it really hard to quantitate. So with refractive index detection, you have to go with isocratic elution. This is just reminding you here of these concepts that we studied before. So it has to be an isocratic elution. We can use refractive index, although it's not very sensitive, but it will be sufficient for our quantitation purposes. All right. But we have some issues with it, and we have to be aware of it as good analysts in the lab, that sometimes your amine groups will be lost because you will get a side reaction of an amine group with a carbonyl group. You know, your favorite Maillard reaction happening here. So it can form this shift base and render this functional group unavailable. And stuff starts building on the column. So in order to mitigate this, we use modifiers. These modifiers are small compounds that have two amine groups. One will react with the silica, and one is kind of like a spacer, is a molecule with two amine groups. one amine group will react with the silicon, the stationary phase, and the other amine group will be available to react with your sample. Okay. There are other modified silica that are used. Diol bonded phase and cyano bonded stationary phase, less common than the amine bonded stationary phase. Okay. Any question about the normal phase? All right. Reverse phase. Now, in reverse phase, what's your stationary phase? Polar or non-polar? The station non. Thank you. Non-polar is the stationary phase. Are sugars non-polar? No. So their interaction with the column will be minimal. They might interact for a very, very brief moment in time, and you will not get separation. All of these small sugars, glucose, fructose, you won't be able to separate them from each other. They will interact very little with the column and then come out very fast in one big peak. So why bother? Why bother? We don't. But if you really have the C18 column and you don't have a helic column in your lab, and you're really, your heart is set on identifying monodi and oligosaccharides using the column that you have, it's still possible. So what you do is you add a little bit of salt. You sprinkle salt in the mobile phase. So you add a little bit of salt, you force these small sugars to react a little longer with the column and kind of shift their affinity to the mobile phase versus the stationary phase, so you get a little bit of separation. The other problem that we have is that some of the monosaccharides will have two forms. We'll have difficulty separating them because of the anomers. So here you have this OH is facing downward, and then the anomer will be the OH facing upward. So sometimes you have these are reversible reaction going back and forth. So, and then you get split peak. So to correct for that, you add a mean group in the mobile phase. You force all of them to be in one form, in one anomer form, so they all come as one peak. So we have a little bit of difficulties, but there are ways if you really want to use reverse phase HPLC. Okay. Now, the anion exchange. Do you remember anion exchange is your stationary phase negatively charged or positively charged in anion exchange? We have a split vote here. Okay, you say positive, you say negative. Who's going to agree with Emma? Stationary phase is positive, yes, because anion exchange, you're exchanging anions between the stationary phase. It's a so you're exchanging those negatively charged components, and then so your stationary phase is positive. And but how can are sugars negatively charged? Is glucose negatively charged? Yeah, no, it's not. But if you put it at high alkalinity, you put it in a solution with the pH is really high, so the OH groups will reluctantly give a proton. So they will give their H and they become O minus. So they are very weak acids. So sugars are very, very weak acids. When you put them in alkaline solution, high alkalinity, then they start giving you a proton from their OH group. Then they become negatively charged. So this chromatography, then anion exchange, you really want to analyze your sugar in an alkaline solution. So they carry the negative charge. And once they carry negative charge, then you can use detectors such as pulse amperometric detector that we talked about in the spectroscopy section, or HPLC section with the different detectors. Okay. So what do you think the order of elution? If you have glucose and if you have sucrose, which one will come out first? Anion exchange, OH groups become O minus. So which will react longer with the column, the sucrose or the glucose? Sucrose, it has more OH minus. So the order of elution would be depending also on the orientation and the availability of the OH groups, monomers first, dimers second. Now, can they be positively charged? No matter what you do, they're not going to carry a positive charge. Even if you reduce the acidity to 2, they're not going to carry a positive charge. However, if you're really stubborn, you can use cation exchange chromatography by using counter ions, positively charged counter ions that will react with the OH groups of your sugars. But here, in this type of chromatography, it's actually a combination of size exclusion and ion exchange. So there is separation by size and separation due to interaction with a positively charged ion. So really complex, very rarely used for monodi and oligosaccharide, but it's not impossible to use. In principle, it can be done. Okay, and here the separation would be mostly on size. So the larger sugar will come out first. Sucrose, then glucose, it's a hexose, fructose is a pentose. So glucose will come first because it appears to be larger in space than fructose. Okay. So mobile phase can have the counter ions like calcium and Ag silver, yeah. And then, or you can use diluted acid where H plus B become your counter ion. All right. Are you full of HPLC? Okay. Do you miss GC? Still chromatography. We can still use gas chromatography to measure sugars. And usually it's used mostly when you want to determine the monomer composition of dietary fiber. So basically the dietary fiber, if you want to know what are the monomers in the different dietary fiber, you have more pectin, more hemicelluloses, beta glucans. So you want to determine those monomer composition, you would break the glycosidic bonds and then you would measure the different sugars in your dietary fiber, for example. That's one major application. But are these monomers volatile? Is glucose volatile? If you put glucose, would it go? No, it won't. So what do you do? What did you do for fatty acids in the lab? Yeah, you did saponification. Yeah, that's fine. But what did you do after saponification? Methylation. So what did you do with meth? What was the goal of methylation? Yeah, to make them volatile and thermally stable. So this is derivatization. What you did is you derivized them into thermally stable and volatile compounds. So you do the same thing with sugars. So you derivatize them, and there are different ways of derivatization. Acetylation is one, silylation is another. Thought you had your hand up. So the way it works, you first convert them to sugar alcohol, And then after they are sugar alcohol, you react them to make, you acetylate them to make them into acetyl esters or silynyl esters. Then these become volatile and thermally stable. Then you can analyze them by GCFID, your favorite method in the wild or wide world. Just seeing if you're still paying attention. So GCFID is normal. The flame ionization detector is a very common detector. You use it in the lab, and then you would need an internal standard. Just as a reminder, your internal standard will be chemically or structurally related to your compounds, but does not elute at the same time, and it elutes within the analysis time. And then here, an example of what type of column you'd use. And then this is mannose, glucose, galactose with the internal standard. All right. Do you have enough of chromatography? Or would you like more? You get it? Yeah. Yes, choose. You want more? No more. Okay, no more. See, you got a choice. Okay, all right. So now we'll move into polysaccharide analysis. I shouldn't say polysaccharide, should I? Is all dietary fiber polysaccharide? What wasn't the polysaccharide? Lignin. Thank you. See, good. I'm just testing you. All right, so starch is a big component and also dietary fiber. So we will talk about how we determine total starch. And also we're going to bring you back to that degree of gelatinization and degree of retrogradation, which both can be analyzed using one method. Not at the same time, but the same method can be used for both. All right, so starch, qualitative analysis. So iodine and starch gives you blue color. So if you on a test, if you have yes or no starch, you can put drops of iodine, and if it turns blue, you have starch. That's a quick method of determining whether or not you have starch. Also, in later class, we're going to talk about some chemical reactions for fat characterization that involves iodine. And then there's going to be titration, and starch is used as an indicator because there will be iodine in the reaction. So it's useful. This reaction between iodine and starch is useful. Another qualitative analysis is microscopy. Different starch from different seeds have different morphology. So you can identify starch using the microscope to determine their morphology. Quantitative, which is why we're here, is enzymatic reaction. So starch is converted into glucose. How, I don't know if there is a slide there, but without looking at your slide, how would you convert starch to glucose? Using enzymes. What enzymes do you think we can use? Amylose, absolutely. We can use alpha amylase. So alpha amylase it's an endoenzyme. So it's going to chop down the starch into a bunch of maltodextrin. How am I going to get glucose? You remember that enzyme? Did you cover enzyme in food chem or not yet? All right, you probably saw this somewhere. Okay, so what you see here is alpha amylase. Alpha amylase chops, it's an enzyme, so it just chops from inside of that big molecule of starch. But then you get a bunch of maltodextrins with different sizes. If I want to get glucose, I need to use glucoamylase enzyme. That chops, it's an exo enzyme, it chops one glucose unit at a time. You have other enzymes you could use to speed up the reaction, and this is pollinase. It's a debranching enzyme. So the alpha amylase, if we want to bring back a little bit of the chemistry here, it breaks glycosidic bond. Do you remember what's the glycosidic bond here versus at the branch?
4 versus 1,6.
Thank you. Alpha 1,4. So amylases are mostly specific, alpha amylase, mostly specific for alpha 1,4. Pollinase is specific for alpha 1,6. But alpha amylase has some specificity to alpha 1,6. It does break it, not as efficiently, but it does break it. So you don't always need pollinase, but to speed things up, you can put the debranching enzyme. And then beta amylase breaks 2 units or 3 units at a time. It will come in, the importance of this will come in another assay. Usually you don't use beta amylase for total starch. Commonly, your kit comes with alpha amylase and glucoamylase for that analysis. Sometimes some kits have pollinase just to enhance efficiency, but it's not needed. Okay, so then you produced your glucose. So when you produce your glucose, then now I need to figure out a way to measure glucose. You could use the enzyme combination that I talked about, hexokinase and dehydrogenase, but a very common kit comes with glucose oxidase and peroxidase. The glucose oxidase, it oxidizes the sugar, the glucose. And in the presence of oxygen, you get a peroxide and you get this gluconolactone. Not important. What you want is the peroxide. The peroxide, you reacted with a dye. The peroxide will oxidize the dye in the presence of peroxidase, oxidizing enzyme, and gives you an oxidized dye that is colored. And off you go, you measure your glucose. This is the most common kit for starch analysis. Okay. Now let's talk about a degree of gelatinization and degradation, retrogradation. And that will be the last thing I'm going to talk about. So degree of gelatinization. So starch, you have raw starch. And then let's say you want to determine the impact of different time temperature combination during cooking or any other process on gelatinization of the starch. So pollinase, which is a debranching enzyme, and beta amylase, they don't act on raw starch. They don't act on retrograded starch. The starch has to be gelatinized for these two enzymes to work. So there you go. So you take your starch that you want to determine how much of that raw starch got gelatinized. You put your pollinase that debranches, you add beta amylase that produces maltoses and maltotrioses, which are reducing sugars now, and you measure reducing sugar content by, you can choose Smoothie Nelson, let's say. The more maltoses and maltotrioses you have, the more gelatinized starch. So you always have your control. You start with your raw starch, you measure nothing. You won't get anything. And then different time temperature treatment, and then you measure maltose and maltotriose. Now you did your process and you want to determine, well, like kinetics of staling or retrogradation of starch in different products. Then you know that it's already gelatinized. Now you want to determine what's the degree of retrogradation. So retrogradated starch, pollinase and beta amylase will not work. So you will get less maltoses and maltotrioses than fully gelatinized starch. Okay, so that's why the same method can be used for both. With degree of gelatinization, the higher the maltoses, maltotrioses, the more gelatinized the starch is. Whereas for retrograded starch, the less the maltotrioses and maltoses, the more retrograded the starch is. Of course, you run standards and there are calculations and percentages, but we're not going to go into that details, but this is for you to know. Okay, well done. Talk about dietary fiber. Do you want to say it? Okay, bye. I'll see you on Friday.